This is more kind of what you should expect.
Okay.
Here's your starting material. What's the product? And you should be able to evaluate all of the pieces of that given information to say, this is what I think is going to happen. Okay? I will note that I did just erase the name of the compound. You're still technically responsible for naming, but that becomes less of an important aspect behind it. So if we looked at this system, how do we decide what happens? What do we see?
Negative charge.
Okay, so one thing that should stand out, hopefully, is that you've got a negative charge. And if you've got a negative charge, what is that thing likely to act as?
A nucleophile.
Or
Or your electrophile. Oh.
can't act as an electrophile, because to act as an electrophile, it must accept more electrons. If it's negatively charged, the likelihood that it can accept more electrons is slim to none. Okay, but what could it do with those electrons? It could donate those electrons to a positive atom other than hydrogen, nucleophile. Or if it donates those electrons to a hydrogen or to an atom that is hydrogen, now it's acting as a base. So looking at this, how would we decide whether it was acting as a nucleophile or a base?
What it's gonna react with.
Okay, so you could push to what it's reacting with. Okay, do we have both hydrogens and electrophiles in that molecule?
We have hydrogens for sure.
Okay, so there are hydrogens, so we have the potential to act as a base. And then do we have anything electrophilic?
If chlorine were to leave,
Okay, so let's lean on that a little bit.
become an
Okay,
electrophile.
so, and you volunteered nucleophile for the iodine, and your explanation was because it is negative. Nucleophiles do not have to be negative. They're negative, which means it's a giant red flag that they are nucleophiles, but that's about it. Okay, but you don't have to be negative. To be a nucleophile, what do you have to have?
Electrons you can donate.
Electrons you can donate. Okay, which means lone pair electrons, or, believe it or not, pi bonds. Because pi bonds are higher energy p orbitals. Those could act as nucleophiles as well. Okay, so that's broadening the class of nucleophile as a definition. It's an electron donor. We don't care necessarily where those electrons come from as long as there's electrons to give up. Okay, if we move to the electrophile, because now you're spinning back and say, okay, to act as a base, we need hydrogens. We have tons of hydrogens in that molecule, right? And we could quickly go through and just label some. Okay, so we've got lots of hydrogens potentially in here. What I'm trying to show are all the quote-unquote unique hydrogens. They would be different from each other. So we could go through and say, well, maybe it's going to act as a base and remove one of those hydrogens. We'll push on that in a little bit. Okay, but before we go into that, okay, we ask the question is, could it be an electrophile? Okay, so we have the potential for it to act as an acid because we have hydrogens. Okay, that's a bit of a narrow definition. Okay, because all you're saying in an acid is it has to have a hydrogen. Okay, we're going to come back to that. To act as an electrophile, what do we need?
Something that's going to accept.
Accept electrons. Okay, and where you leaned initially was if the chlorine has left, I'd then have a carbon that was missing electrons, and that would be an electrophile. Okay, just like nucleophiles, okay, sharing electrons, you don't have to be positive to be an electrophile. Okay? And that one becomes harder to go through and explain. Because if that carbon acted as an electrophile and we had, electrons share inwards, you should immediately call out a problem with that, and which might be why you're saying you wanted the chlorine to leave first. What's the problem with the iodine sharing with that carbon?
It exceeds its octet.
It exceeds the octet. Oh, we can't exceed the octet. No, we absolutely can. Unit 1 said don't exceed the octet. Okay, because we're looking at static structures. The structure does not change in Unit 1. What happened in Unit 2? It changes. Okay, in Unit 2, it's quote unquote can exceed the octet. We can exceed the octet as long as at the same time that we exceed the octet, we fix the octet. It's a simultaneous system. Okay? So if the chlorine left at the exact same instant the iodine shared, we've never technically exceeded the octet because both of those things happen simultaneously. Okay? That simultaneous versus, as you were initially suggesting, stepwise, is now putting emphasis on how does the reaction happen. Okay? At this point, we didn't even cross the bridge of how yet. We were just saying can. Okay? And in that can, what we're looking for is those positives and negatives. Those don't have to, when I say positives and negatives, I'm not saying necessarily formal positive and negative. I'm saying partials. Okay? So do we have positives and negatives? Yeah, we do. So we have the potential for our iodide, our I- to act as a nucleophile or a base. We have the potential for that carbon-chlorine structure to act as an electrophile or an acid. Does that narrow the field for any of the chemistry that could come out of this?
Not really.
No, in fact, actually, I would argue it's not a not really. It opens the field up for all the chemistry. Okay, so how do we narrow the field? Well, to narrow the field, we have to know some more information. Okay, so now the question becomes, what information would you like to look at?
Can I ask a question really quick?
Probably.
Before you
Yes.
should I move forward with this? Could the chlorine be the electrophile in this situation if it were to leave? No, because it's satisfied.
Okay, so currently that chlorine has its octet. To act as an electrophile, we'd have to accept electrons from somewhere else.
So
So
something else would
this
happen.
iodide, could the iodide share with the chlorine? So I like this because what we're pushing at is what are all the possibilities? So could that iodide share electrons with the chlorine? What would happen to the chlorine? Bigger issue. It would exceed the octet. Okay? Exceeding the octet isn't necessarily inherently bad, but what we must acknowledge is that we are going to exceed the octet, and therefore, what else must we do?
Something else has to break away.
Something has to break away. So now the question is, what breaks away? On that chlorine, we have lone pair electrons and a carbon. Right, the sigma bond to the carbon and lone pair electrons. Would we expect lone pair electrons to just float off on their own?
No.
Right, and I phrased that horribly because no one's going to say yes to that. Okay, but remember, our electrons are inherently unstable and cannot exist on their own, which means no electrons will ever just float off. That just doesn't happen. Right? So if I can't touch the lone pairs, I must then be saying that the electrons in that bond need to go to the carbon.
Oh, and then carbon can have a lone pair.
And then carbon has a lone pair, which is an awesome statement because what you just drew a conclusion on was based off of the drawing of what these arrows mean. Did we draw that?
No.
We didn't. So why am I calling you out for being awesome?
I feel like you're yelling at me.
I'm not yelling at you.
Because we know
I'm
that
excited.
if you're breaking the bond essentially because carbon's then taking what it's sharing with that chlorine.
So again, let me rephrase it. Okay, and it's not that you're wrong. Okay, you are able to analyze the structure of the product of these arrows. Have we drawn that structure?
No.
No. So what is so amazing about what you have done?
I can see it.
You drew that structure in your head. That's amazing. Okay? That's where you need to be. You need to be able to look at that structure in your head to say, what does it look like? Okay? What's the next step behind that?
What does it mean?
What does it mean? And to that, what does it mean? Is that a good thing? Should I be able to do that? Okay? That's a harder question, and because it didn't sound like everybody else was on the same page as Sydney was with drawing the electron, oh, it has lone pair electrons, we should probably draw that out so that we could all see it and so that we could all have that conversation on whether that was a good thing to do or not. Is that okay? Or do I need to show the carbon as a C explicitly? What's that?
That's okay.
That's okay. What else happened? We still have that chlorine. What did that arrow from the iodine to the chlorine show?
It's bonding with the.
Cool. That arrow is showing a bond forming between the iodine and the chlorine.
They'll each have one less lone pair. For iodine.
Okay, and iodine has one less lone pair. So that's what we're showing is happening. That's what all of those arrows mean. The question now becomes, is that a good meaning or is that a bad meaning? Said another way, remember, all reactions are equilibrium. They can go forwards and they can go backwards. Is this a thing that should go forwards? Or is this a thing that is, oh, hell no, this should go backwards? Oh, hell no. And to decide that, we've got to be able to rank what's going on between these and decide what is good or bad about either of those systems. So when we think about our chemical reactions, what's the number one thing our chemical reactions should do?
Make products. Be stable.
What defines stability? Where do you start looking for stability? Charge. So what we need to go through and do is look at the charge on the reactant side, look at the charge on the product side. Okay, so what's the charge on the reactant side?
The negative.
It is negative. What is the charge on the product side?
Also negative.
Okay, so is there a difference there?
No.
Okay, and if there's no difference, we might say, well, then there's no reason to go forwards or backwards necessarily. Okay, so we could say it's fine to go forwards. But do we stop at charge? Bless you. No. What do we move to next? Size. And when we move to size, what we're looking at is the atom that is holding said charge. So I'm comparing iodine to carbon. Is there a difference in size?
Yes.
Ooh. What is that difference in size?
Iodine is bigger.
Iodide is bigger. What am I trying to write? Size. How does that change the stability, right? And then asking yourself, is that right or not? Ideally, we'd look up at the periodic table and be like, oh yes, iodine is lower on the periodic table, and because we remembered back in Unit 1, the very first thing that we were told that we needed to know was trends for size, we could look at the periodic table and quickly assess that iodide is lower on the periodic table and therefore is significantly larger than carbon. So yes, there is a size differential. How does that change the stability of that negative charge?
Bigger is more stable
Bigger is more stable. Why?
because is it the orbitals?
So you could look at
They have
orbitals.
more,
It's like if the size of it being bigger can hold the charge better.
But why? And it's a hard kind of question to answer. The way that I would use it is effectively personifying it. Okay? Our electrons are now able to occupy a larger space. If you have more space to roam, you're happier. This is why, what do we do to people who do things wrong?
put them in a cage.
We put them in a cage so that they feel bad for being put in a cage and they don't do what they did, what we decided was wrong. Okay? The same thing kind of happens here. Okay? So iodide is more stable than the carbon as a negative. So what does that suggest about the direction of our reaction?
It's going to favor the reactants.
That size evaluation says the iodide is favored, which means
It's more stable.
it's more stable, which means
Low energy.
what's that?
Low energy.
Yeah, it's lower energy.
It makes more things.
Is it making more if I'm saying the reactants are favored? What we just attempted was, well, what happens if it does this? This is what happens. We just decided that what happens shouldn't happen. What does that mean about our initial process for moving on this path?
Not a good process.
We were wrong. This was a bad process. Okay? Or this was a bad action. Whether it's a bad process is different. This isn't a bad process. What we're trying to evaluate is what things can change, how and why. And we push on it and we look at it and we evaluate and be like, well, dang, that sucked. This becomes probably the hardest thing with organic chemistry because you need to be able to push on things and be like, well, crap, that was wrong. But the only way you discover, crap, that was wrong is by doing it on your own and doing this evaluation.
Doing all the options you can think of.
Yeah.
What's the best option? What is
Yeah.
stable?
How much time does that take?
A lot.
A lot of time. But by finding the dead ends, you don't discover them on the exam. If instead you don't find the dead ends now, you will discover them. There's no way around it. It's going to happen. The question is when. If you find the dead ends now, you don't replicate them on the exam. If you don't find them now, you will find them on the exam. Right? And the problem is you will have wasted your time doing a process that resulted in a structure that was not valid. So you have to do the practice to find those dead ends.
And then in practicing, you will be able to recognize, like, oh, I know that these two things are going to react.
Right? And so therein lies
Better off.
kind of the next dilemma. How do you know whether it was a good thing or a bad thing? Well, that's the process of looking at our reactivities. That's the process that we just walked through. Okay? Charge, size, electronegativity, all of those things. That's what you're evaluating at each and every single one of these stages to decide what happens. Okay? Do you have to do that? No.
No,
But then you have to do enough practice that you recognize what's going to happen without having to draw it out. So you either do a whole bunch of practice where you've seen all the answers, or you do a whole bunch of practice that you've seen all the dead ends. You get two paths, same amount of work. Your choice. Okay? For me personally, you need to find the dead ends. Because a well-written multiple choice exam has all of the dead ends as valid answers or as distractor answers. So you have to be able to dig into those.
Can you explain what the dead end was in this reaction?
Right? The dead end. We said this is what's going to happen. We formed the negative carbon. Was the negative carbon better than where we started?
No.
Nope. What does that mean? All the work that we just drew up there is wrong. That sounds like a dead end to me. You didn't progress forwards. Okay? And we might have different definitions of what a dead end is, but I would argue that's a dead end. You tried a bunch of work and it went absolutely nowhere.
Yeah. So something that didn't have a charge before has a charge
After
it's
could very well be a dead end. Yeah. Okay? And that is more challenging. As we continue to dig into these things, you will encounter cases where we get exceptions is a little bit off, but you will encounter cases where looking at charge size and all of that didn't quite work. There was some piece missing. You had to think a little bit deeper. Okay? Exceptions, you should memorize.
Would that be the same with, like, things that do better negative?
Well, what makes a better negative? Charge, size, electronegativity, resonance. Okay. So looking at those rules helps you to discover what makes a better negative. There are certain scenarios where you get effectively a stacking effect of lower quality things that overcome a higher quality thing. Okay. The analogy that we could push back to is when we talk about solubility or melting point or intermolecular forces and all of those things. We could look at two structures and say intermolecular forces, water versus naphthalene. Because I don't expect you to know the structure of naphthalene. And that's a horrible way to draw it, but close enough. Water versus naphthalene. Well, water has hydrogen bonding. Naphthalene has London dispersion forces. If we ranked those based off of forces, water has stronger forces, which means I would expect a more solid phase of water in comparison to naphthalene. That does not make water a solid. I'm just saying it should be a more solid than naphthalene. And yet, if I look at water and naphthalene at room temperature, naphthalene's a solid. Water's a liquid. So the complete opposite of that interpretation came into play. Why? There's another contributing factor. That other contributing factor is the size of naphthalene. There's more atoms. More atoms leads to more of those interactions. They may be weaker, but I get more weaker interactions. Okay? Can I break a piece of spaghetti? Yeah, that's pretty easy. Okay? But can I break an entire package of spaghetti?
Yeah.
I can. You can. I'm gonna say I have tried that. It doesn't work very well.
Yeah, that's how you, if you're, you gotta do it over the sink because a bunch of stuff will fly
Yeah,
out.
don't talk to an Italian then. Italians will get kind of pissed at you. Okay? And breaking that, but that breaking the entire package is significantly harder. Okay? Even though we're looking at weak interactions between them. Okay? So it's trying to find a system that allows you to rank all the way through. Okay? So we go back to this. We said the iodide was a nucleophile and the other structure was an electrophile. Okay? In particular, we said the electrophile was the chlorine. Does that mean this molecule is not an electrophile? No, it just means the chlorine is not an electrophile. The iodide, since it's only one atom, we didn't invalidate iodide acting as a nucleophile because we don't know what it's reacting with. Okay? So that one test didn't result in anything potentially useful for us other than to see that that didn't work. Okay? So what should we do now?
Try it with the carbon being the,
Okay? So now the suggestion is try it with the carbon.
and the chlorine as the leading group.
Now the chlorine would act as our leaving group. Okay? And if we now push through and look at this, what changes?
Chlorine is by itself.
Cool.
The iodine, it connects to that carbon. It makes a bond with that carbon.
Cool. What's different about what I've drawn as a product versus where we started as reactants?
The chlorine is negative.
True.
The
So making sure that we've fixed our charges is good. Our chloride is now negative.
iodine is positive. It's neutral.
Why is iodide neutral?
Formal charge.
So you could go through and calculate formal charge. Or we remember our bonding patterns for our halogens. All of that stuff from Unit 1 comes screaming back at you because you have to be able to have those systems in place.
I think
What else
that's
is different?
fine. Oh.
Ooh, because there's still something else different. So that's fine. You can say, oh, there's nothing fine different about it.
No,
There's
no,
still
not-
something else different.
Not that there's not something different, I just think that's a fine.
Okay, we'll come back and evaluate that. Because this one does get significantly harder. Something different about the reactants versus the products.
Do with the wedges that you
Why would we use wedges and dashes?
like, to help us visualize the way the bonds are moving, or the connectivity.
Cool, let's put all of that information together. And so what you're saying is that that carbon in our starting material is not a planar molecule, and we're trying to better show where those groups are oriented in space relative to the rest of the molecule. Okay? Cool. I used a bunch of fancy words, but I would argue you said the same thing. Okay? Cool. Did I show those in the product?
No.
Does that mean in the product that that orientation in space isn't relevant anymore? Do I need in the reactant to be showing all the wedges and dashes to show that orientation in space? So why do we bother to show orientation in space?
Could be completely different.
Sort of.
Because they're pushing against each other.
So we could say to try and better show the tetrahedral structure, yeah, okay. Purple dot in our starting material. Everybody see it? How many bonds does that purple dot have?
4.
4, just like the red dot, right? And yet, I don't see wedges and dashes on that one. Why not?
They're implied.
There are implied hydrogens, but why? Why is it okay to imply those hydrogens, but it is not okay to imply the wedges and dashes for the other one?
Because of is it priority?
Why priority? What does priority have to do with anything?
It's a chiral center carbon.
There it is. Okay. That starting material, that red dot, is a chiral carbon, which means the relative orientation of those groups in space is important. It does matter, because if I swap the wedges and dashes there, what we're doing is switching between right and left hands. And that does make a significant difference, because if I reached out to shake your hand with my right hand versus my left hand, your response is different. Or we get weird, awkward handshakes. Okay? What does that mean? Well, what's effectively happening in this reaction? That reaction is reaching out and making a handshake. You're making a connection. When you make that connection, that could have an effect on the overall product. So when we go to the product, do I still have that chiral atom at the end?
Yeah.
I do. And because I do, that wedge and dash now does become important. And the question becomes, how do I draw those wedges and dashes?
Would it still have the same priority because you have like carbon hydrogens, carbon
So the
hydrogens,
individual
carbon
atom labels or priority labels, 100%, yes, they have the same priorities. Okay? That doesn't change the wedge and dash. That has no effect on the wedges and dashes. So what I'm asking is, should that iodide be wedged and that CH3 be dashed? Or, should the CH3 be wedged and the iodide dashed? To your priorities, 1, 2, 3, 4, those aren't going to change in either of those systems. How do I know which one should be correct? That's a really challenging question. That would almost be like it's dependent on how the reaction worked. You mean almost like a repercussion of how your mechanism ran. Yeah. Yeah, that's exactly it. Okay. So we would have to dictate based off of how we're trying to represent this reaction, whether that should be wedged or dashed. Okay. And that's going to be determined based off of how we have decided that mechanism runs. Okay? And that's an interesting dilemma, because we don't get to decide what the chemistry does. The chemistry does whatever it wants to do. We have to predict it. So we have to be able to look at this and go, this is how the reaction is going to work, so that this is the answer. So we have to be able to look at the pieces of this reaction and say that the curved arrows I'm using are indeed correct, or they are not. Okay? That's a really deep process, particularly considering we don't even know if this is the reaction we should be doing yet. Okay? This was one nucleophile, one electron. We didn't look at the acid-base reaction yet either. Okay? So how do we know? Should that be something we look at now, or should we wait?
We look at what now? Or
Whether we should be identifying that wedge dash, be that specific with the product. Or do we want to wait a little bit?
Well, if we wait and then we go through the acid-base process and then determine that that's the best, then we're just not.
We wouldn't look at this. You're right.
Yeah, we would just ignore that.
We will eventually.
But we don't have to worry about it for right now.
That's kind of your decision. Okay? Do you think the acid base is something that you need to be looking at? Do you know why the acid base is or is not valid?
I would say the acid-base wouldn't be the best
Why?
because you would take a hydrogen from a carbon.
I can take hydrogens from carbons.
I know, but that's like not how it usually happens.
Yeah, why not? Why? So let's try that. Because what you're doing, right, and maybe other people are doing it also and not vocalizing, but what you're doing is at least projecting, saying what you're seeing in your head and making conclusions. I don't know that everybody's doing that. So let's take the acid base for a second, okay, and let's run that.
Because like how would you determine what hydrogen would be dipping out from the carbon when they're all?
An equally valid question, okay? And you hovered out with a statement there and said, well, they're all the same. They aren't all the same.
Well, no, not the same, but I mean like the same, like carbon, hydrogen. It's all the same bond.
Whoops, that shouldn't be an R group. How would we decide which hydrogen is the one we're talking about in this acid-base reaction? So I'm going to make a change. Entirely new question. Everybody see the change?
Yeah,
Which hydrogen do I remove?
the one connected to the oxygen.
How'd you do that so fast?
Because oxygen is more likely to be chilling by itself than carbon is.
Why?
Because of its electronegativity.
Bingo. So what you end up doing is charge, negative carbon, negative oxygen. They're both negatively charged. There's no difference. I can move to size, oxygen versus carbon in the same row. No difference. Oxygen versus carbon, electronegativity. There is a difference. Oxygen is more electronegative, which means it is better able to hold the negative charge, which means the conjugate base is more stable, which means that hydrogen was the more acidic hydrogen. Ah, you twit.
But
Why is asking the question, which of these hydrogens more acidic, any different?
because they're all connected to carbon.
Okay, so work with me here. If we removed it, we'd have the black as a negative carbon. We'd have the red as a negative carbon. We'd have the blue as a negative carbon. We'd have the purple as a negative carbon. Or sorry, carbon. Sorry, I drew that one wrong. And for the sake of brevity, I'm not going to do the green one. I did it again.
We did.
C. So we could look at charge, they're all negative. We could look at size, they're all carbons, so they have the same size. We could look at electronegativity, they're all the same electronegativity.
Oh no.
Which means we'd now have to move to a molecule effect. So when we're looking at those negative carbons, we would then have to take a step further out and say, well, what are those carbons connected to? In being connected to something else, do I now have the potential for resonance? And you should be able to propagate and decide, do I have resonance? The only one that you should be even remotely tricked about would be the purple one. Okay, and if you're like, well, I think I'm tricked about all of them, then guess what you need to do?
Practice resonance.
You need to draw all of those, extend those structures out, and be like, can I draw resonance from this black negative carbon? Nope, okay, it doesn't have resonance. Can I draw resonance from the red carbon? Nope, okay, well, it's not that one. So you have to do that practice. Remember back when we talked about resonance in Unit 1 and I said you needed to do the practice? You're like, I don't need to do the practice. There it is. You either do it when I tell you to do it so that you don't have to do it now, or you do it now. Those are your choices. The purple one is tricky because I'll get students going through, well, can't I do this?
Well, no, because isn't it just gonna keep, you're just gonna keep going around and around and around and around?
If I push these arrows, that's what I would produce. So is it just forcing to continue to go around and around and around? No, it is not. It's not forcing to go around and around because I haven't affected that top left pi bond. That pi bond is not affected by this arrow. We're going from the atom to the bond and from the bond to the atom. Okay? Could I then say, can I do more resonance? Yeah, we could try and do that and go from the atom to the bond and the bond to the atom. And then yes, we would continue to draw multiple resonance structures. And if we draw multiple resonance structures, what does that suggest about the stability of that structure? Yes. And if it's very stable, that would be a good thing. And we'd say, it's the purple one. That was the acidic hydrogen. Okay, but before we push into that, what we've got to lean into is be like, what happened here? This goes now back to our atomic orbitals. When we look at the hybridization of these atoms and try and figure out where that pi system is, let me squeeze it up here. We'll try and draw it for the sake of the recording. We're going to take that ring, which is flat, and I'm going to turn it on edge and pull it out of the screen kind of at you. P orbital, p orbital, p orbital, p orbital, p orbital, p orbital. So my electrons are spinning all the way around that pi system. That's just the benzene. If we now bring in that negative, where is that negative? It has to be in another orbital. Guess where that orbital is? Perpendicular to the plane. If it is perpendicular to the plane, does it overlap with the pi system? Mm-hmm. No, which means even though I can draw arrows that make it look like it's part of it, it's not part of it.
It's just going around.
These electrons, so our pi system, there's our benzene, there's my p orbitals. Okay, just pretend the pen goes around 6 times and I have 6 hands. Okay, and we do this, so we can see the p orbitals kind of up and down. That's what this is trying to show. Right here, where are the electrons? They're chilling out here. To get them to overlap with the white pen, what do I have to do? I have to rotate the whole atom to bring those electrons up to do resonance. But by doing so, what did I do with the pen electrons?
You moved them.
I moved them out of resonance. Effectively saying those lone pair electrons are not in the pi system. They will never interact with it. Is that easy to see? Hell no, it's really hard for people to go through and pick up and see. But ultimately what that means, I can't do resonance. So if none of those do resonance, now what do I do? Is that it? And I say, well, all of them are equally acidic?
No, you look at.
Yeah, there we go. We move to induction. Okay, induction is a molecule effect, but looking at an electronegative group being nearby. So if I go through, the black atom, black carbon, has an electronegative group 1 bond away. Okay? The purple one is 2 bonds away. Which one is more acidic? Which one is felt more by the chlorine?
The black carbon.
The black one versus the purple one, which means that negative charge on that carbon is getting drawn to the chlorine stronger than the negative charge from the purple one. And if the negative charge comes into the structure, does that make it more reactive or less reactive? To react, what must happen?
You gotta have a strong pull.
enough?
Or push.
To react, where must the electrons go? To shake someone's hand, where must my hand go? To their hand. But if I have a strong pull in my chest, pulling my hand back, where does my hand go?
Back to
Is that easier or harder to react?
harder.
That is harder.
So
The
you want-
electrons get drawn into the structure. That makes it more stable, less reactive. So would that suggest, in comparing black to purple, black was more acidic than the purple one? That's an inductive effect. Okay. OChem2 is talking about induction right and left. We'll probably see that pop up again towards the end of this semester. Okay. I can't guarantee this statement, but the answer is never induction.
Like we'll never get there.
It is so rare. It's the bottom of the list as far as stabilities go. When you're looking for reactivities, induction is very rarely ever the answer behind it unless it's being explicitly asked about.
Unless you're like
Right.
focusing
So
on
what does that ultimately mean? Between these, the carbon that's closest, sure, is induction, so we can pick the negative carbons. Let's just say the negative carbon. Okay? To decide if that reaction happens, what do we then have to compare it to? So we've now established that there was a there was a difference between all of those hydrogens, right? So I'm going to erase all the colored hydrogens. And we're just going to bring in, call that a green hydrogen now. Our I minus would come in, pick up that hydrogen, and dump the electrons there, right? And I would form H bond to the I. Now that I've predicted my products, what can I go through and do? Compare. What do I want to compare? And this is a case where you can actually look at a couple different things.
Are we going to compare the iodine to the carbon?
I would argue that's the best place you should go. You should look at the charged species. So negative carbon versus negative iodine. They both have the same charge, so no difference. What's the next thing you move to? Size. Is there a difference in size between iodine and carbon? Yeah, there's a significant one. Iodine is significantly larger, which means it's more stable, which means
The reactants are favored.
the reactants are favored. All of those arrow pushings,
Dead end.
dead end. Why else is this a dead end? This goes back to Gen Chem. And when you talked about acids and bases, in Chem 130, or 151, if you were lucky enough to take 151, maybe 152, you should have been told something about HI.
I don't remember.
HI is by definition a strong acid. So now you've been told that. What's a strong acid? Doesn't matter the class, you should have been told what strong means.
Explosive. Unstable.
Unstable, I'll accept that. It immediately dissociates into the ions. You mean it goes back to I minus? Yes. You mean it goes back to the reactants? Yes. I formed HI. Bad. Can't do that. Bad reaction. Doesn't happen. I don't do the acid-base reaction. Okay? If I'm aware of those pieces, I can use them. If I'm not aware of it, I have to fall back on other parts. The HI is effectively a memorization tool that theoretically Gen Chem should have set you up with. If they didn't, did I give you another way to get out of it?
Mm-hmm.
Yeah. Okay. So you have to get used to that process so that you can do what you may already be doing, what Sydney is doing, and holding those structures in her head and starting to make those evaluations. Okay. Whether you're not perfect at it, but you're dang close. Okay. And once you have those pieces there and you're identifying those charge states, you can start making those comparisons to decide whether that was a good or a bad thing. Okay. So what does this mean for us? Cool, that was a dead end, but as a dead end, that was pretty lovely because it's not all of the chemistries now, it's only electrophile nucleophile. It's not acid base. That simplified a lot of stuff. That's pretty cool. Okay, that could work. So we could then go through and say, well, that means we got to deal with this wedge and dash stuff. That wedge and dash stuff has to do with how the reaction worked. Okay, well, that how was using curved arrows. Did we draw curved arrows?
Mm-hmm.
Yeah, we've actually already implied a how on this reaction.
Does it have to do with the size of the arrows?
Nope. Size of the arrows only has to do with distance. Okay, the distance between my drawings. But remember, organic chemistry isn't your drawing. These things are constantly moving. The distance between atoms is irrelevant in our drawing. The length of the arrow has only to do with where you've drawn those structures. And that's entirely arbitrary. So we got two arrows. We'll color code them. We'll call the short one purple and the long one green. Okay. What does it mean with the purple arrow? What's happening?
It's taking electrons.
Pretty vague. I kind of get where you're going with that.
It's breaking the bond and...
The chlorine is taking electrons away from the carbon-chlorine bond.
Yes.
Okay, being super, super, super specific behind it. Okay, where are those electrons located? They're located in the bond between the carbon and the chlorine, and that bond is in front of the rest of the molecule because it's wedged. Okay, what about the green arrow? Back to the purple arrow. Is there any other way I could represent that purple arrow? It's a really hard question, and it'll become more relevant when we look at the green one. We look at the green one, what's happening?
Iodine is sharing its electrons with that central carbon and forming a bond.
Awesome. I'm taking the electrons from the iodine, I am sharing them with the carbon, forming a new sigma bond. Is there any other way I could represent that green arrow?
Yeah.
What do you mean?
I mean, you put it there because that's like the nuke attack and it's going in from underneath, right?
Ah, so interesting. You're saying that this arrow is very specifically showing a location of where I want the chemistry to happen.
Yeah.
I did not show it doing this.
Yeah.
That was a little bit awkward, but you can at least get the idea. Well, why did I not show that?
Because there's more crap up there, so it's harder for it to get through.
Be more specific than crap.
There's more electrons.
Where are the electrons from?
The chlorine over here.
Ah,
and
there it is.
carbon.
That chlorine is taking electrons away from the structure, and because it's taking electrons away from the structure, it's becoming negatively charged. If I have the iodide try and come in from that exact same location, that's bringing electrons from the iodide in towards the chlorine. And what's going to happen?
They're going to repel.
They're going to repel away, and the iodide is going to repel away from the structure. The chlorine is going to repel away from the iodide into the structure, only making the bond stronger, which would suggest the iodide cannot come from the top. It has to come from the backside. Okay? Which is a little bit of an overstatement, and we'll see why here in a second. Okay? So if it comes from the backside, those electrons are forming a bond between the carbon and the iodide on the backside of the bond with the chlorine. Which means when I draw out the product, that iodide bond to the carbon must be shown the opposite direction of the starting carbon-chlorine bond. And because the starting carbon-chlorine bond was shown at me, wedged, I must show the product with that iodide being dashed. That is a natural repercussion of the arrows that we have used for how we're saying this happens. Yes?
Would that then change the carbon next to it?
What do you mean?
Like, so you're coming in from the back, are you then essentially kind of like rotating that forward, so then that's why it becomes wedged and doesn't stay down?
So, and this one becomes hard. You can't really pull it off with a model kit. they'll show pictures in your, I'm gonna say textbook, but that's a bad reference. I don't know that we've actually got the page references set up for that quite yet. It might be in the slides where you see an umbrella. Like an umbrella has kind of that curved shape over the top, and then you've got the stick that you hold on to. When the wind comes in underneath, what happens? It pushes the umbrella top up the other direction. This is effectively the same thing. The wind is coming in underneath from the backside and causing the rest of the atoms to bend away from it. If we use my hand, my leading group is the wrist. We're having the nucleophile come in, and my wrist explodes off the back of my hand, and then these fingers have to bend the other direction away from that new group of electrons. Okay? It's doing what is known as an inversion in your structure. Okay? And because we've inverted the structure, it very commonly inverts the stereochemistry. Not always, because it requires that there was stereochemistry there, and it requires all the 1s, 2s, and 3s in your priorities come out the same. But in the vast majority of cases, you're looking at an inversion. Okay? An inversion both in the structure and an inversion in stereochemistry. Okay? Should this reaction have happened? How do we decide that?
We go through and compare charges and
Yeah, we'd look at the charges of our iodide versus the chloride, and we are very quickly going to run into an issue here. We're looking at both of those being negatively charged, so we can't evaluate charge, so we'd move to size, which one's bigger? Iodide, which would suggest
that is more stable.
it's more stable as the reactant, and our reactant is favored. Okay? We do encounter an issue here. This particular case was a bad example for me to pull up because we're looking at different aspects behind this reaction. This particular reaction structure system was chosen as an example so that you could have a discussion about the two different mechanisms and the repercussions of them, okay, without having to bring in other secondary issues. So we're forced into the statement of this happens, make it happen. Okay? Star Trek, make it so. No, okay, fine. Okay? So in this particular case, we're forced into that statement. Okay? How would you know you're forced into that statement on an exam?
Practice.
A little bit of practice. I would argue it's more of the question. So look at the question. Does the question say, predict the product, and is one of your answers no reaction? One of your answers is no reaction, then you should say no reaction. If none of your answers is no reaction,
You know something.
you need to do something, and you need to pick the best something of those options. This would be a case of that best something.
So like in this case, though, no reaction wouldn't be an answer?
Yes.
Okay.
Because what we're trying to do is talk about the repercussions of the reaction. So it was a bad example for me to pull up. Okay? It does get more complicated than that, because what we're comparing is the stability of the nucleophile to the leaving group within this system. Okay? And that is heavily solvent dependent. With it being solvent dependent, it becomes very tricky to nuance, and it's usually a question I try to dodge because it's beyond, I would argue, beyond the scope of what you guys need for this class. So you would see the questions formatted of this happens, do the best that you can with what we've got. Okay? If we're pushing to repercussions, the repercussions we're dealing with the different mechanisms. We ran this as a reaction. What reaction did we run it as?
It looked like an SN2 to me.
So,
That's-
lovely answer for a different question.
Yeah.
I asked for the reaction. The reaction is not SN2, the reaction is substitution. Okay? Once I know the reaction, I could then ask, what's the mechanism? Okay? And now I'd have to know the different mechanisms that could happen and how the substitution occurred. Okay? In this particular case, we're talking about a substitution reaction, and how we decided to represent this reaction, or this particular one, was through an SN2.
Because you're making and breaking.
We are making and breaking simultaneously. Okay, there was another option. What's the other option?
Nucleophile attack.
what you're trying to describe is the steps that are involved in it, which is okay. The nucleophile attacking is technically not going to work because you would exceed the octet. So you can't have the nucleophile attack first. So it either happens all at once or it happens in steps. And when it happens in steps, since there's only two things, pick one and see what happens. If the nucleophile attacked first, you'd be forming a 5-membered carbon. We can't do that, so we can't talk about the nucleophile attacking first. What do we have to talk about?
The chlorine.
The chlorine leaving first.
Oh, so leaving group or heterolysis?
Right, you're getting too fast for me, but yes. If it leaves first, and we generate a carbocation, and then we'd have the chloride chilling out here with the negative charge. Okay, so that mechanistic step would be a heterolysis because we broke a bond. And then what would the next step be?
Formation, so it's SN1.
The formation of it. So we'd then be making the bond. Okay. If we look at the overall system, what happened was a substitution and we broke it into multiple steps. And when we break it into multiple steps, we call that an SN1 mechanism. The two steps that were involved in that SN1 mechanism were heterolysis and coordination. So we get the same product. Did I draw the product the same?
No.
What did I draw differently?
You didn't draw the wedges and dashes.
I didn't draw the wedges and dashes. Is it necessary to draw the wedges and dashes? Is that still a chiral carbon? Yeah. Which means I should be more specific with the wedges and dashes. So, how should I be more specific? The deciding for the first one, our SN2, that the iodine came in from the backside and was therefore dashed, had to do with evaluating what's happening within our mechanism, looking at our curved arrows and thinking about those molecules in three-dimensional space. Which means what do we got to do for the SN1?
Same thing.
The exact same thing.
So because in the first step the chlorine is pulling it away, is it still going to pull that carbon forward, or is that carbon just going to?
Well, that's an interesting question for the sake of the recording, because I think I can point. Maybe I can't point. Oh, I can point. So what you're saying is that chlorine pulled the electrons away. Does that mean that carbon, our CH3 back here, necessarily comes forward? Well, how many groups of electrons are around that carbon?
There's 3.
There's 3. And if we have 3 groups of electrons, what's the shape? Trigonal planar. Okay, which means, are they all in the same plane?
No.
Planar. Yes. That's why we call it trigonal planar.
Yes.
So did it necessarily get pulled forward? Yes, it did. Okay, it did get pulled forward. Okay, did it get pulled forward so that it's wedged? No, it got pulled forward so that it's in the same plane. Okay, that first step ultimately isn't the one that's important. When we talk about what happened in our top case, the one that was really driving our reaction, or the thing that we were concerned about, was the iodide and how the iodide came in and reacted. Well, where's the iodide in our second case? It's coming in and reacting. What is it reacting with?
The positive carbon.
Where is the positive on the carbon?
On top of it.
You can hate me in a second. No. It is not on top.
Above it.
It is not above. Those were the same answers. I'm not that mean. What'd you say? Below it. If it's not above, it must be below. No.
Oh,
What was that?
Both.
It's both above and below. Why is it both above and below?
Because it's the atom that's charged.
What's holding the positive charge on that carbon?
The lone pair.
There's no lone pair. An empty p orbital. That p orbital is both above and below the plane of the structure, which means that iodide can come in and put electrons into the top lobe of the p orbital. It could equally put in electrons onto the bottom lobe of the orbital. Because it is equal, what does that mean we have to do?
Decide.
Sorry,
Oh.
it's worse than that. There is no decide. Both products.
Oh, you have to draw both of them?
You get an
Show it.
equal amount of both of those products. Because there is no preferencing, you have to specify both. So when we're talking about repercussions for the different mechanisms, if I'm running an SN2, I need to know that it's running backside attack, and I have to worry about that inversion of stereochemistry. Okay? And by have to, I only have to if there's a stereo center. If there's no stereo center, I don't care. Okay? If I think I'm running an SN1 mechanism, I have to acknowledge that I get two products, not one. And the relationship between those two products is?
Resonance?
It's not resonance. Yeah, you could call it inversion.
You're talking about like distereomers or
You got the right idea, but wrong word.
identical.
They aren't identical. These two structures will not superimpose. These are enantiomers. Does that mean you always produce enantiomers? No, because if we had another chiral atom in there that didn't react, now they're technically diastereomers. Okay? So you get two products when you run the SN1 if it reacted with a chiral atom. Okay? Or it produced a chiral atom. We have to be aware of that.
But if it doesn't have a chiral, then you're not.
Then we don't have to stress about it. Okay? And so that becomes some of the kind of issues within our chemistry when we're talking about organic chemistry, is that sometimes we have to worry about all of these problems, sometimes we don't. And it's largely dependent on what circumstances we're under that we care to look at or not. Okay? Does that mean every time you run substitution you have to worry about chirality? No. Okay? Because chirality is one of those deeper complex aspects behind it. Okay? To differentiate between SN1 and SN2, I want you to be able to tell me that SN1 is running in two steps. That's equally valid. That has nothing to do with chirality. That has to do with acknowledging that it happens in two steps. Okay? I want you to be able to acknowledge that SN2 is happening in one step. Yeah. Okay? So you can get different levels of questions all the way through this. I want you to be able to tell me the iodide acts as a nucleophile. Does that have anything to do with whether it's SN1 or SN2? Not whether it's either one of those, but that iodide is acting as a nucleophile? Yeah. All you need to know is the nucleophile. It can't act as a base. Why not? I formed a strong acid. Okay. Okay. So working through these two kind of examples sets us up with probably 20 different questions that I could ask. Okay. All at differing levels. Okay. And where the challenge with organic chemistry comes in is that if I ask these kind of same questions, except I threw on an extra ring, that's a horrible drawn ring. Oh my God. But I add an extra ring to this, what happens? What happens to the chemistry? It changes absolutely nothing about the chemistry. But what happens to student success?
Plummets.
Yeah, it goes through the floor. Oh my God, I have no idea what's going on anymore. Because you get too hung up in those secondary structures. When we're talking about this reaction, all we really cared about is that we had a leaving group connected to 1, 2, 3 other things. That was it. That's all we cared about. The rest of those things We're hangers-on that are just there because structures change. Why would the structures change? Well, can a nail be used to put a leg onto a table? Yeah. Can a nail be used to put a stud into a wall? Yeah. Can a nail be used to hang a picture? Yeah. Do they all have varying different roles and responsibilities? And yeah. But ultimately the same chemistry is happening behind each of those systems. So what you have to be careful on is to acknowledge what's the chemistry behind it, not the structures. That is challenging to go through and do, particularly if your mindset is, I need to memorize. Focus on the chemistry. Look at those arrows. Look for those negatives. Look for those positives. That's where the chemistry is located. All right, can I delete everything?
Really
Go ahead.
quick. So, say we're like trying to differentiate, we get through all this, is it SN2 as SN1?
That's just a shitty hard question, but yeah, go.
Because it's, or no, maybe that's not the question it's asking. Like, so for example, if it was like, just this is happening, and then just this is happening, then it's the heterolysis
So-
coordination. But because it's happening at the same time, that's how we know it's the SN2.
What I think you're asking is how would you look at this and differentiate which mechanism was happening?
Yes.
You wouldn't.
Okay.
This isn't one to do that on, because this was specifically picked as an example that allows both mechanisms to happen so that we could see what the end result would mean. Okay, that's the point behind it. So what we would have to do is look at all the components that contribute to substitution reaction. Well, what are the components to a substitution reaction? As a hint, there's 4.
Like the heterolysis.
Leaving group,
Oh.
substrate, nucleophile, solvent. There are 4 components to the overall reaction. Of those 4 components, we can ignore, for the most part, leaving group. Okay? Because you need a leaving group for a substitution reaction to happen. So if you're trying to decide between SN1 and SN2, it has a leaving group done. Okay, who cares? You would have to look at the substrate. Well, what things are going to favor a backside attack versus 2 steps? Okay? Well, if I'm going to do a backside attack, what would I expect of my substrate? What should be on the backside of that leaving group bond? Big things or small things?
On the backside, small thing.
Small things. So what I would do is look at where my leaving group is and say, what's on the backside? Are those big things? That's not SN2. That's going to push SN1. They're small things? That's probably SN2. So what you need to do is now come up with, well, how do I classify big things and small things on an individual substrate? Well, that's primary, secondary, tertiary. That's the point of those classification systems. So you now have a language to reference it as opposed to saying big things and small things. Right? So that's what you would be pushing to. So your substrate could give you some information. Unfortunately, the substrate here is secondary. The secondary, actually this one's tertiary. And as tertiary, it should never do SN2 because you put 3 big things on the backside. SN2 shouldn't happen. Why is it used as an example? Because they're trying again to show the difference in the stereochemistry. So we're saying this does SN2. You don't get to choose. If I tell you to draw it as SN2, you do it. That's how it works. Okay? If I give, here's a structure, tell me what it does, that's a different question. Because I'm not forcing you. You have to decide. You have to put that interpretation into it. Okay? So that's where what you're looking at is those summaries. I already forgot what I was going to say. Oh well. Those summaries, where are those summaries? This. Okay? Where you would look at your substrate, your leaving group, our nucleophile, our solvent. Look, they're all listed here. Okay? And for SN1, what kind of substrate do you want? Well, this is where, having studied it and looked at it, you could be like, the substrate I want stabilizes a carbocation. Well, what carbocations are more stable? Tertiary, secondary, or primary? Tertiary. Good. How fast should your response be? About what she said. If you're like, well, I don't know that. That's something you need to go back and review. We talked about the why behind that so that you could fall back on the why. Okay? So if you see a tertiary substrate, you say, it's SN1. Okay? What kind of nucleophile do I have? If I have a strong nucleophile, that's SN2. If I have a weak nucleophile, that favors SN1. So what I would go through and do is look at all of the individual reactions. Well, this is running SN1. What things help it run? What things don't help it run? And what you effectively create is a table similar to this. And what you would do is just look at the check marks. So if I saw 1 check mark in the column for SN1, but 3 check marks in the column for SN2, my total is 1 versus 3. Which mechanism should I do? SN2, because there's 3 things that I can evaluate that say it should do SN2. That's how I do SN2. What if I come through and I get 2 check marks for SN1 and 2 check marks for E1, and 0 for the others?
You do something wrong.
No. You do both.
And just see what is the best.
No. You do both. There is no way to differentiate it. Both of those would be potential products. So that particular reaction is going to run both a substitution product and an elimination product. In a multiple choice, what are you going to see? Probably the substitution product, probably the elimination product, probably a none of the above and a all of the above. And you'd be in the all of the above category. Technically, you wouldn't put all of the above below the none of the above, but you get the idea behind that.
A and B.
Yes, or not A and B. Neither A and B. Make sense? Okay. So what you're starting to ask are good questions, but now you're starting to push into, well, how can I ask a question about that on the exam? That's good. Okay. You should be trying to get to that kind of point. But what you're following through is effectively this aspect. That's a really deep level question. Because first I need to, do you know what a nucleophile is? Do you know what makes it strong? Do you know what makes it weak? Do you know what a leaving group is? Do you know what makes it good? Do you know what makes it bad? Do you know what the different substrates are? Tertiary, secondary, primary. Do you know what the different solvents are? Protic, aprotic. Which one supports which mechanism? Okay. Heat. What does heat support? Okay. So this grid, just the blanks alone, that's a multiple choice question. Okay. And within this, do you see anything about stereochemistry?
No, but if you were to have 2.
Because all of those stereochemistry questions are complications or results or lessons that come after you've established what mechanism it is. So this one slide covers you 20 questions. Now throw the complications for each of those reactions, and you got another 4 or 5 questions. Okay? All of it stacks, all of it builds. Any weakness early on is going to continue to manifest. Keep working backwards as you work forwards. You got the ability. Review what you missed. Continue to work. You have this. And I'm going to take silence to mean we're done because we need to be done.